It's a pleasure to introduce the next speaker, Professor Joy Mitra from ISET Thiruvananthapuram. Joy did his undergrad from Presidency College and then went on to do an integrated PhD at the University of Science in the lab of Professor Rao Chaudhary. And subsequently, he did his postdoc at Queen's University in Belfast. So Joy came back in 2010, joining ISET Thiruvananthapuram's faculty in physics. And currently, he's a professor of physics at ISET Thiruvananthapuram. So Joy's interest spans a large range, and he's also, of course, has enormous fame, attained enormous fame as a popular speaker of science. And so we are really lucky that we could get him to give us a talk on how light is produced.
Thank you, Shitabro, and the organizers for inviting me here. And it's brilliant to see you all here. Hopefully we'll have some fun time on the matter of light. I'm Joy, and I'm from an institute called ISEF, Indian Institute of Science, Education and Research, which is in Thiruvananthapuram, which is the capital city of your neighboring state, Kerala. Okay, and here is pictures of the campus. It's a beautiful campus that we have right up in the foothills of what is known as locally the Ponmudi Hills. Yeah, and a lot of wildlife right next to a reserve forest. A lot of elephants, wild boars, yeah, and the likes of them running throughout our campus. Yeah, we have literally electric fences to keep the elephants out, and and we have really vastly encroached upon their space. Yeah, but that's our campus, and I'll also for the students here, especially the high school students, if you aspire to be a scientist. Yeah, so these are the kind of programs which the institute runs. Yeah, we have our flagship a 5-year program which is known as the integrated BSMS program, which gives you a Bachelor of Science and a Master of Science degree in all the basic sciences, as well as new areas of data science, earth environmental sciences, and so on. And we also run a master's integrated PhD and a PhD program for more advanced or mature students. Today I'm going to speak about light. Okay, and light, as all of you will appreciate, is absolutely integral to our existence. Okay, the last line especially, photosynthesis, which is the source of food, yeah, which we survive on, the entire planet survives on. It is triggered by light. Okay, so the question, obviously, what I try to answer or put across to you is, how is light generated? Okay, we do appreciate that light is very important in today's world of fantastically super fast internet. Much of the communication is through optical fibers or light beams being sourced from the earth to the satellite, bounced back to different places on the earth. We have constellation of satellites, the Starlink, which across the world, if you have heard of it, provides internet access. Yeah, the entire communication is essentially through light. It is very different from what it was a few decades earlier. When I was a kid of your age, yeah, internet was in its nascency. Yeah, it was just kind of starting to mature. Much of the communication which I knew about, okay, actually happened through copper wires. Okay, and electromagnetic and long distance, it was electromagnetic signals like radio waves. There was radio communication, but the last mile connectivity pretty much went through by copper wires. And that has its own set of problems. Okay, why? It got replaced with optical fibers, which has very low loss, yeah, and there are various other advantages, which has really sped up our communication. Yeah, you literally consume a huge amount of data today simply because, the amount of video calls, the amount of videos, the amount of reels that you see at fantastically fast speed, which would not have been possible had we stayed back with copper wires entirely. So that's how important light is. And celebrating in the International Year of Light back in 2015, this is what the UN had to say about light, that light-based technologies promote sustainable development and provide solutions to global challenges in energy, education, agriculture, and health. And we got a very hard but first-hand view of how it really enabled education, especially during the COVID pandemic, which kind of, really devastated much of our learning school experience. I'm sure it has affected all of you. Yeah. And we saw how we didn't have to go to the school, but the school almost came into our living room, yeah, by video conferencing, so on and so forth, all enabled by light. Okay, that's how important light is. And this slide shows you a list of Nobel Prizes which have been awarded from 1907 up to 2014 on various aspects of light. Some to do with, for example, you can see photography, some to do with optical metrology, the workings of the eye, the Raman effect, which most of you must have heard about, yeah, which is a phenomena connecting light. Then you have the laser, you have laser spectroscopy, femtosecond spectroscopy, which deals with like super fast responses of systems. Yeah, the fluorescent protein GFP, which has revolutionized biomedical imaging, the optical fiber, the charge coupled device, which is called this is not coffee day, but it's charge coupled devices. Yeah, by which many of our cameras run. Yeah, that's how we take digital images of the cameras. Yeah, and then the icing top it all was the blue light emitting diode. Yeah, which allowed us to make LEDs which are white in color. Yeah, because the evolution has really matured our eyes to see the best with white light. So the red LED and the green LED came much earlier. Yeah, literally decades earlier. But we couldn't produce white light because the blue part was missing. And that's why it was given a Nobel Prize in 2014 to the discoverers of blue light. A bit more of motivation on the history of light. Yeah, for the billions of years that in the past, like I've said 4 billion BCE. I mean, prehistorically, the only source of light that animals on the planet were familiar with was the sun. Till the discovery of fire. Okay, and fast forward to around 500 BCE. Yeah, humans tried to tame that fire, like it domesticated animals. It tamed fire also. Yeah, it was no longer uncontrolled, but in the form of oil reservoir lamps. Yeah, in China, in India, in Mesopotamia. Yeah, we have this discovery of signatures of discovery of oil reservoir lamps. Then obviously came the candle. Yeah. Then came fast forward really a lot of time. This is 400 BC when the candles were there, and then we come to 1809. Okay, with the discovery of by Humphrey Davy of the arc lamp. I don't expect you to read. Don't try to read. It's just the main headings which are more important. Yeah, the arc lamp, which was in 1809. Yeah, and then with the discovery of mineral oil, yeah, and kerosene came the lantern. Yeah, and henceforth the turn of the last century, 1879 and 1900 onwards came the Edison bulb. Okay, and then over the last few decades, the latter half of the 20th century, yeah, I'm sure you're quite familiar with all these terms, the neon light, the sodium vapor lamp, which might still be there in parts of the streets of Chennai, yeah, the yellowish, orangish yellow glow, yeah, that's the sodium vapor lamp, the fluorescent tube lights, which you might have at home before you had the LED tube lights come in, and then you have the laser, the fluorescent bulbs, and finally the LED. Yeah. If you look at this fantastic over the millions of years, different forms of light. Yeah, I'll tell you that we can almost draw a line here. Yeah, this versus these. And can anyone tell me, or do you have any idea why am I drawing a line here? Yeah, that all these can be classified into one type of light or one origin, Yeah, all of these can be classified into something different.
And natural light, second part.
Nothing very natural about kind of, yes, okay, that's good. Yes,
Heat is separated.
right, brilliant. Yeah. So all these sources, you see, all these sources, all these sources up to here, is what is known as incandescence. Okay, you take a body, okay, you heat it up. Okay, you heat it up, and the sun is the same. You have a reaction going on. It's brilliantly hot, and as it heats up, it starts emitting light, and that is the term given to incandescence. And this is a bit of a physicsy blurb. If you don't fully comprehend the thing, it doesn't matter. Okay, and we call it technically that for incandescence, we have radiation, which is the light going out at all wavelengths. Light going out is in equilibrium, is in thermal equilibrium with the matter itself. So therefore, there is a one-to-one connection between the temperature of the object and the light which is going out. Okay. So just to demonstrate what do I mean by that, what I'll do is, here I have a small a pin, okay, and I have a source of light here. I don't know how much you'll be able to see, but what I'm going to do is, I'm just going to hold it here, this steel thingy, okay, and if I hold it in the blue part of the flame, again, caution, if you are trying such tricks, you have to be extremely careful, and you can notice that I'm also holding it with a pair of tweezers, which is made of steel, so that my hand doesn't get burnt by the heat, and what you should be able to see is that this bent wire, is faintly glowing now. I don't know if you can actually see it, but it is actually red hot, at least from my vision, from this distance, it is red hot. It has started to emit light of its own. So you see the temperature of the object, and the light it's emitted, is connected one to one. And I did this by heating it up. The flame itself, you could see either blue or the yellow part of it, simply because the particulate matter there was raised to a particular temperature. It was burning due to the oxygen in the atmosphere, right? It is combustible, and you have the oxygen around it. And once you took it across its combustion temperature, it started burning, and you could see it because it was emitting. And that's exactly what happens. All these forms of emission of light, the sun, this is exactly what I did here, a normal fire, they are all incandescent. As opposed to that, the latter half of the examples I gave you, come from a phenomena which is known as luminescence. And luminescence is a very different beast. You do not have to raise the temperature. And that's why LEDs are so much more energy efficient than the older arc bulbs. Because there, light and matter is not in thermal equilibrium. The light emitted do not arise from simply because you have heated it. But then how does it emit light? It emits light because the material is excited. We'll come into what do I mean by a material is excited. Okay, Shitabra also alluded to excitation of the nerve cells. It is absolutely similar. So this is excited material, not in thermal equilibrium with matter. LEDs is one example, and you have more fancier. I don't know if any of you have party shoelaces which are fitted with LEDs which glow in the dark, and you go to a dance floor, it looks just fantastic. So these are the things which we will. So we are going to understand a bit more about what is luminescence and how different varied form luminescence comes in. So what do we mean by excited material? Just to give you an idea of what do I mean by an excited material, this is a Jenga block, here. And if I keep it on the floor, I will call this that it is in its ground state, simply because it's lying on the ground. That's ground state. Okay, it doesn't have any energy, it can't do anything on its own. I lift it up, I push it here, okay, and you look at it, obviously it gained potential energy, right? It has a lot of potential energy given by this difference. Yeah, it has a potential energy. And what do I mean by that? It has energy because if I give it the slightest impetus, it can actually fall, right? By falling, what did it do? It went back to its ground state. It lost its energy, right? The potential energy it had, it lost it. What did it get transformed to? Kinetic energy, right? Now, I'll make a difference that energy might also be lost as light. It can emit a photon, right? So, the energy of the light that is emitted depends on how high I actually raise it. If I raised it only here, it would have fallen still, but the amount of energy would be smaller, right? And for light, energy and wavelength is again unequivocally related. Yeah, longer the wavelength, lower the energy. Lower the wavelength, higher the energy, right? And you are pretty familiar with the visible part of the spectrum, which starts from blue, yeah, and goes up to the red. Blue has the lowest wavelength, highest energy. Red has the highest or the longest wavelength and the lowest energy, right? So just remember this, and that should be brilliant. Okay, so this is the mechanism. So now the thing is that this is an excited material. You take it somewhere from its ground state or base state, so some higher energy state, and then let it freely evolve, nudge it a little, yeah, just like I did to that wooden block. Okay, however, how I nudge this block or how I actually make it go up can vary from situation to situation. I can physically raise it, okay, I can have an elaborate system of a pulley raising it, yeah, I can actually kind of have a air blow pump blowing air below it, which will kind of float it up to a higher energy state. So you can imagine there are various ways of making it excited, yeah, but the moment it drops back, de-excites, it is going to emit a photon of that energy difference. Okay, so two things to remember. That's an excited material. Okay, that's an excited material. The mechanism of excitation or the trigger can change how I raised it. Okay, when it falls back to its ground state or low energy state, it will emit light, and that light I'll call luminescence. So the trigger can actually change, or the mechanism of excitation can actually change, and that defines or classifies the kind of luminescence prefixed with the mechanism of excitation. Okay, and the first example that I am going to discuss is known as chemiluminescence. Chemi comes from the word chemical. Okay, so that means the excitation was done chemically. And one of the most fantastic and fascinating examples of chemiluminescence is actually bioluminescence. How many of you have heard of the word bioluminescence? Brilliant. Okay, so let's look at some examples. The first example are fireflies. Okay, the fireflies, I'm sure most of you have seen fireflies out in the dark in a bit of wilderness, and they kind of glow in the dark. Yeah, these are sea planktons. Yes, dinoflagellates, the blue planktons. Yeah, this is the Juhu beach in near Bombay. Yeah, certain oceanic conditions leads to plankton blooms, and then you can actually see that in the Arabian Sea. This is a gnat larva in a cave, and the secretion of that emits light. Okay, here you have a millipede which goes on emitting light. Here you have an earthworm which glows blue. Here you have foxfire mushrooms which glows orange and blue. And here you have what is famously known as the flashlight fish, where below each of their eyes they have fluorescent dyes, pigments, okay, and they can actually blink it by controlling the amount of chemicals going into that patch and going out of that patch. And what do they use it for? They use it for exactly how we use light, communicate signals between each other. Okay, and all of this brilliant light, which is in the biological world, essentially comes from a very basic oxidation reaction, which is known as the luciferin-luciferase reaction. Okay, so if you are interested, it's a very fascinating field. You can look up what is a luciferase reaction. Yeah, and it's an oxidation reaction, and it gives off light. Again, the mechanism is that you mix the chemicals, which excites a part of these chemicals or the atoms or its electrons to a higher energy state, and then it spontaneously de-excites, giving off a characteristic light. Yeah, there is a brilliant documentary on BBC by David Attenborough, and it is called the documentary is called Life That Glows. Yeah, so if you get a chance to see that documentary, clips of it are available on the YouTube. Okay. But if you get ever to see, if you try to figure out a way of getting hold of the full documentary, it's rather fascinating. It certainly piqued my interest approximately 10, 12 years back, I think this was produced. Okay, that's chemiluminescence, where a chemical interaction actually does the excitation. As I said, the prefix is the trigger. Okay, but there are there are other forms of chemiluminescence. Bioluminescence essentially is a form of giving out light when a solid dissolves into a liquid. Again, if you're interested, you can just look up the term. I'm not going to go into the details of what is bioluminescence, but as the solid dissolves into a liquid, it starts giving off light. Again, it's a form of chemiluminescence because the chemistry or the chemical interaction does the excitation, and then it gives off a characteristic light. What we are going to look at a bit more detail is what is known as photoluminescence. Then, photoluminescence, by now you do realize the trigger is light itself. Light of one wavelength does the trigger, okay, and out it gives light of either the same or another wavelength, yeah, mostly a different wavelength. And this is the phenomena which is actually, you must have seen fluorescent paint. Some of you might have t-shirt with fluorescent prints which glows in the dark, yeah. And phosphorescence, this watch that I am wearing is actually has a fluorescent phosphorescent dial and hands, so that it glows in the dark. Throughout the day, it absorbs light and stays in an excited state, and very slowly it goes on emitting photons, so that in the dark, in the night, I can perfectly see the time. Yeah, so that's phosphorescence. And how did phosphorescence come about? Phosphorescence, very interestingly, was reported even in in ancient historic times. Okay, in Chinese text, in Indian text, in Latin American text. Sorry, and how did it come about? Because they saw that if water was stored in certain wooden cups, okay, and this particular example is from only the 16th century, from a wooden cup which actually was known as the lignum nephriticum. The name, obviously, nephri, has a medical connotation, and that's why it has the name lignum nephriticum. But anyhow, this water stored for long periods made of this particular wood took on a bluish tinge. Not only that, depending on what colored light you actually viewed it in, yeah, it actually changed its color or hue. So what does it mean? That you see, the trigger was photo, the trigger was light, yeah. So depending on what wavelength of light came in, it used to give a different color of light out, right? So the similar thing was rediscovered in the 19th century with the fluorescence of chlorophyll. It's the same material which gives the green color to the leaves, and this was done by a physicist called Brewster. This was investigated by Monardis, was a physician, Boyle and Newton later in the 16th and 17th century. A very similar thing happened in the 19th century with the chemical quinine. Have any of you heard of the chemical or medicine called quinine? Quinine is used for the treatment of malaria. Okay, and again, it is a natural product. It's a natural product, and this gentleman in the United Kingdom, Stokes, actually saw that if he took a vial of quinine, okay, and placed it in the red part of the spectrum, it was looking red. In the yellow part of the spectrum, it was looking yellow. Green, it was looking green. Blue, it was looking blue. But if it placed it beyond that spectrum, which today we call the ultraviolet, it suddenly glowed brilliantly blue. What it meant was, he obviously didn't realize what was the origin fully, But what he saw was that a colorless liquid was suddenly starting to emit light. The mechanism is again the same, that the trigger is the ultraviolet light which was being absorbed, exciting the molecules of quinine, and then leaving it to de-excite, which was giving off the blue color. What he did notice was something very important, which we today call the Stokes law. The emitted light was almost always at longer wavelengths than the incident light. So it would absorb higher energy, but release slightly lower energy. Yeah. And this is known as the Stokes shift, and today we call it the Stokes law. Yeah. So if you want to look at a history of fluorescence and phosphorescence, before the emergence of quantum theory, there is a very nice article on Journal of Chemical Education, which came out in 2011, and rather informative of the whole story, the historical development. Now, as I'm repeatedly trying to tell you, that all this is nice. This is all being observed. This is observational. But how do you make sense of it? Why does it happen? How does the, almost always, if you have very discrete states, okay, like atomic states, it can absorb the same quanta of energy and release the same quanta of energy. It will be a loss in quantum efficiency, perhaps, but not in the energy or the wavelength of light.
So it can be the same wavelength, but not
as high. So exactly the number of electrons that you had excited, you had excited, all may not undergo radiative transition. That is true. So the quantum efficiency can be less, the intensity can be less, but energy-wise, it will be less. Yeah, this depends on how discrete the levels, the ground state and the excited state is. But in the vast majority of the cases, you will see Stokes' law for any material systems. Not very specially prepared. You will see that. Yeah. Okay. So let's come to now. But why does it happen? Okay. And all this was being observed in the 16th, 17th, 18th, 19th century, which was before the advent of quantum mechanics. And unfortunately, this phenomena of luminescence, excited states, even though I showed you with a Jenga block and you'll say it's just classical physics, Newtonian physics, you should be able to explain it. It's not that simple. And people, and obviously we understand there is a step here and there is a ground here. But we are speaking of matter, right? How does this connect, energy states connect to states in matter? That matter can be described in terms of energy states only came with the advent of quantum mechanics, okay, which I do understand is slightly beyond your brief. You have probably heard of the word quantum mechanics, but you don't really appreciate fully what it is. But what it does tell you is that matter itself, on its own, for the example, this material itself, can exist, or the composition of this material, like the electrons, the protons, the atoms, can exist in various energy states. It can be in its ground state. It can be also in higher excited states. You can imagine this energy scale like a ladder. Okay, this material or the components of this material can reside on either the lowest rung of the ladder, okay, or any of the higher rungs of the ladder. If it is in a higher rung of the ladder, then it is in an excited state. If it is in the lowest rung, it is in its ground state. Again, the same understanding as with the Jenga blocks here. Right. So here you have a ground state. As I said, it is like a long ladder with various states. I'm just drawing two states, and you have a ground state and an excited state. And I'm giving you a very general example that atoms or molecules have these discrete energy states. That's the conceptual thing, which is a step change, and which quantum mechanics tells us how to obtain these energy states, so on and so forth. So what happens if I shine light on it? If I shine light on it, let's say there was an electron in this, what I call the ground state. It's like the Jenga block lying on the ground. And it can absorb that energy and go up to this excited state. Okay. And then what happens is, after some time, it was there. And when I nudge this Jenga block, it will fall, right? So it can spontaneously fall back. And that fallback, its loss of energy, will be given by light. That's what I've been saying. And that's why, since the trigger is a photo, it is called photoluminescence. And the same thing can happen in not in atoms or molecules, but in more crystalline systems called semiconductors. Again, something which you are very familiar with. Yeah, semiconductors are there all over your system, all your mobile phones, your laptops, everything. Even your watches today run on semiconductors. Everything. The cars have literally thousands of chips inbuilt into them to do the control of the car. In case of semiconductors, the thing is a slightly bit different than the H. That's right. So that's a difference of symbol. You can see I have given an H cross and omega. That's right. And omega is essentially, so H cross is H by 2 pi, if you just look at it mathematically. Okay, so nu and omega is again related by the same 2 pi number. So it is equivalent. So in the case of semiconductors, the thing is a slightly bit different. The ladder, instead of having very narrow rungs, like very discrete states, these states are slightly broader in energy. That's all that happens. And we call them bands. Okay, instead of having very narrow energy states, we call them bands. But the phenomena is perfectly the same. You have a lower band, just like a lower state, and you have a higher band, which is a higher state. Pumping light, it excites, and then it can also de-excite, giving off light. Now, it so happens, and this is the fun part of semiconductors, which is not, it happens, but not that easy in atoms or in molecules, is that you see, for the light to come out, what I really needed was an electron to be in an excited state. I didn't have to doesn't really care how you take it up to the excited state. Okay. Light was used here, an incoming photon was used here to excite it. But I could have excited it otherwise also. So very soon people realized that I can actually inject electrons directly into the conduction band, into this higher band, directly, okay, which will then fall down and give you light. And this is what an LED does. Okay, this is very simply what an LED does. And therefore, it is called electroluminescence now, simply because the trigger has changed from photo to electricity or electrons. And therefore, we call it electroluminescence. Yeah. The very important part of this game is that the energy of the emitted photon is exactly dependent on what is the energy difference between that high state and the low state, right? So, you see, from here, I'm going across the VIBGYOR, right? The entire visible spectrum. Energy is increasing in this direction, wavelength is increasing in this direction. So, wherever the transition is taking place, if it was a larger energy, then it would emit more towards the blue-violet, with a higher energy and a longer and a smaller wavelength. And if the energy gap is narrower, then it would actually emit towards the red with a longer wavelength. Make sense? And so therefore, we kind of now tacitly understand that there is an equivalence between the energy and the wavelength of light vis-a-vis the energy difference between the states. Right? Okay. So now let's come to the next part of my demo. Here I have a red LED. Yeah, you can see it brilliantly going red. Okay, this is a semiconductor is there, a semiconductor chip is there. Okay, of a particular energy gap, which is getting translated. I am pumping in electrons through one side and sucking them out from the other side, and somewhere in between, these electrons are getting de-excited. They are dropping down from the higher state to the lower state, giving off red light. Okay. So if I actually now, so that's red. Yeah, that's red. If I take another LED, this is a yellow LED, and obviously, as you expect, if I connect it, it will glow yellow. It will glow yellow, orangish yellow. And the understanding is that this is a slightly different semiconductor, which has a higher gap, energy gap. And therefore, it is giving off light of a higher energy, a longer wavelength, shorter wavelength. Make sense? Now, the fun begins. But all this you tell me at your level, then Joy is telling me stories. Okay, it is exactly as good as any other myth or fable. Okay, give me some proof that whatever you're telling me is correct. So that's where the fun starts. Okay, so now I'll tell you If the energy difference changes between the higher state and the lower state, then obviously the energy of the emission will change and the wavelength will change. So which means if I start off with this guy and somehow I manage to change its energy difference or the gap, yeah, it should start, if I can increase it, then it should start going to this side. So what was red should turn orange or yellow. What was orange or yellow should turn green or blue. Make sense? Yeah. So if I show that, I'll be giving you an indirect evidence of, look, I might be actually speaking the truth. Okay, let's see if I can do that. And the easiest way of changing this energy difference in the same material, yeah, is by changing its temperature. Okay. So where does this energy, all these ladders, energies in the solid come from? It comes from the arrangement of the atoms. You have heard of crystals, yeah, where the atoms are actually arranged in a very symmetric way. Yeah. And what happens if I change the temperature of an object? It will either contract or expand depending on, yeah. And that, you see, that arrangement of the atoms is going to be distorted, right? If it is brought closer or it is expanded, right? And therefore, now it is probably not very difficult for you to imagine. Think of the ladder, yeah? If I heat up a ladder, yeah, the gaps between the rails can change, yeah? So that energy scale associated with the crystals will also change, yeah? So to do that, what I am going to do is, to drastically change temperature is not a very easy thing. What I'm going to do, and okay, so here you have this liquid nitrogen. It's just liquefied nitrogen. Okay, it's very cold. Okay, so I'll definitely not urge you to do anything yourself. Okay, what I'm going to do is, it's the same red LED. Okay, I'm going to dip it here. It is 77 Kelvin. Okay, cold. So if I put my finger in, it is going to burn. Okay, so that's why it's dangerous. Okay, and what I'm going to do is, I'll put on my gloves first, which is very important. Put on my gloves first, and then I'm going to kind of, so now it's at room temperature. It's not really hot at all, yeah, because this is luminescence, not incandescence. Yeah, it's not hot. Okay, I can touch this LED bulb. Yeah, I couldn't have touched that filament though. Yeah, it would have burned. And I'm slowly going to put it in, and it's red in color, and let's see what happens. You saw what happened? That red turned into orange. There is, take these curves. Other ones are a bit thick, so that's why I use control of it. That's far more dangerous. So if I just warm it up, it will slowly regain its reddish color. And if I push it back again, into this, push it back again here, you will see it slowly going further orangish. You can see almost yellowish orange. Yeah, I'll leave it out and we'll come back to it a bit later and try to see whether it has regained its reddish glow. Okay, I'll take another one which is, I think, yellow in color. Okay, so if I start on the yellow, it should go towards the green or the blue, right? So let's see if that happens. Yeah. This is the yellow LED. And if I push it in, You can see it fantastically. Oh, it's probably comped off. I cooled it too much or too fast. I'll go to a new one. Yeah, it does happen. Oh, it's there. Or just a loose connection. Yeah, so, it's green already, but it will grow greener if it's probably something is going wrong in that. Okay. So that one was green, that one was red. Okay, and now I'll do, but you did notice that two things happened. One was the color shifted. That means the energy increased, yeah. The wavelength became shorter, energy became higher, which essentially meant that the gap between those energy states was becoming larger and larger, right? So that when the photons were de-exciting, they had to cover a larger energy difference and therefore give up light of a different energy. Okay, so hopefully this now gives you a bit of confidence that all my blabberings has an element of truth, which I'm sure you will kind of appreciate far more when you go to do your higher studies, yeah, in science or otherwise. The other thing which one of the gentlemen told me there was, not only does the energy change, but it also does it actually becomes a bit dimmer, right? So therefore you can see the efficiency of the diode is also compromised. To show you that how that actually pans out, this is a slightly stranger diode. Again, very common, nothing very uncommon about it, but a slightly different diode. And it actually is a combination of three diodes. As you can see, it's a combination of three diodes there. There is a red, blue. Okay, so there's a red, blue. Yeah, not three, it's two. Red, blue, and it goes on blinking. Yeah, it goes on switching between the two, the red and the blue. Okay, now let's see what happens to this guy. I'll need a bit more of nitrogen. Pour it out. So here you have this diode. Now obviously this diode has two colors. Okay, the red and the blue. Yeah, two different parts of the spectrum, and it also switches. Yeah, so it has a timer circuit inbuilt into it. Another bit of electronics. Yeah, which allows you to switch after a certain period of time, repeatedly. Yeah, right. Timer circuits are important, right? Why? Where do we use timers? Yes. Okay. Anywhere else? Timers. Without timers, nobody would be very happy. Think about it. Why are timers important? Okay. So let's cool this. Yeah. Let's cool this. I'll put it in, and you can see the blinking. Can you tell me what is the rate approximately? Let's say, okay, 1 second to half a second. I'll give you. Okay. Let's see what happens. It changes color and the rate increases. I've taken it out. Yeah, it'll take some bit more time to actually go back to the color. So it's becoming faster and faster and faster. Right? Yeah. So you can understand two things. The part of the electronics, yeah, the part of the electronics which is controlling the timer part of the circuit, yeah, that recovers much faster. But the part of the electronics which was connected with emitting light, that has a much delayed response. So the reset time is much longer. Yeah, and it takes much longer to go back to its original colors. It's almost come back actually. Yeah, I'll do it once more. So it became orange and more blue, yeah. Why does the rate? That would be a bit more difficult for me to explain to you at this stage. Yeah, but I can tell it to you. So do you have some idea of how time can be controlled electrically? I is what is I and what is Q and what is T? Current. Yeah. Okay. So what is okay? Fine. Yeah. Fair enough. So if you have which class are you in? In 12th standard. You have heard of a capacitor, resistor circuit yet to study? Okay. So the simplest electrical circuit which actually can give you time, okay, or anything to do with time, is a resistor and a capacitor in series with each other or parallel to each other. Yeah. And the product of this, R into C, yeah, actually gives you time. Okay. So therefore, in a circuit, to make you understand at this level, if I can change the resistance of the device or the capacitance of the device, I can actually change its time. And something similar, very similar is happening here. Okay, it is becoming slower simply because the resistance is increasing of the material, which makes the electronic circuit. It's obviously not an electrical circuit, yeah, but the resistance of the material is actually changing, and that's why it's time. The associated time is also changing. Okay, I'm probably not the best person to answer this question. Okay, yeah, it's rather fascinating stuff though. Yeah, but we do understand from much of Einstein's work that space and time, yeah, are related objects in a certain scheme of things. All right. So it is interconnected, and therefore, yes, time can be controlled, or time does change. In terms of gravitating objects. Yes, that is true. How it goes about? Yeah, it is a bit more. Okay, just coming back to the whole story, just to prove my point that indeed it should have all come back to its red. It's kind of nicely warmed up now. Yeah, so you can see it has come back to its red, original color. Yeah, where I started. So therefore, you see, this is one way of interesting way of showing how luminescence comes. Okay, and obviously it is done without heating the object. Therefore, it's extremely energy efficient. Yeah, and that's how it has been embraced in today's lighting solutions or communication solutions. The other very interesting example of electroluminescence is what is known as the aurora borealis or the aurora australis in the northern and the southern hemispheres, which are recently in the news. Yeah, if you have followed the news, yeah, because the brilliant activity of the sun in the solar cycle, which has peaked now, we have brilliant displays of color. Brilliant displays of color over northern Europe, northern US, near the poles, basically. So that's another example of electroluminescence. I'll end my whole thing with discussing some of the more quaint forms of luminescence. You can also have mechanoluminescence, where you actually use mechanical energy to create luminescence. The best known examples are triboluminescence. If you take a nice piece of sugar crystal, yeah, and press it and hammer it or press it, it'll break, it'll shatter, giving off a brilliant flash of light. Okay, and that's triboluminescence. You have piezoluminescence and you have sonoluminescence. And this video here actually shows it's an air bubble inside a water chamber, and look at what happens as the pressure is increased to squeeze the bubble. Yeah, so now the pressure is being decreased, now it is squeezed. Yeah, so as it is squeezed, the bubble collapses, giving off a brilliant flash of light. And the jury is out why that really happens. It's a major area of research, and that's the one of the labs in UCLA, University of California, Los Angeles, who are doing work on sonoluminescence. Yeah, go ahead. That's right. Yes, absolutely. Yeah, so basically how do you control those waves is by controlling the pressure. It's a mechanical aspect. That's all I meant. Okay, you also have light being given out when crystallization happens, which is called crystalloluminescence. Nuclear kind of radiation, yeah, also gives rise to luminescence. Thermoluminescence, cryoluminescence. If you cool an object, you also can get light, and those are the various different forms of luminescence that one might get off. So in some sense, this is known as cold light luminescence, and incandescence is hot light, where you actually heat up material and you actually give off light. That brings me to the end of my talk. Hopefully you enjoyed. I'll take your questions. This is my lab. If you really, and this is the kind of work which which is kind of systems which I work on. I work mainly on light matter interaction, doped semiconductors. I do a lot of imaging in the nanoscale, including biological systems. These are images of red blood cells. Yeah, this is images of fibrins where blood clot forms. This is the image of microtubules and proteins binding around it in a cell, extracted from a cell. This is the surface of a silicon, sample. Yeah, the same silicon which goes into most of your semiconductor devices. Yeah, and these are very generally fascinating, at least fascinating to me. Fascinating images of various things I work on. Yeah, this one. This is a scanning tunneling microscope STM image. Yes, and these are kind of notionally the electron distribution on the surface of silicon 7x7. The RBCs are atomic force microscopy images. They are obviously false. No, the coloration all throughout is false. Yes, everywhere color is false. Yeah, it is only the contrast which makes any sense. Can you see that ray of light? Yeah, it's a laser, and I have that's one ray. I can have 3 rays. Yeah, I can have 5 rays. Okay, yeah. Hopefully it looks nice. Yeah. Okay, and obviously Shitabro was discussing formation of images and the optics of the eye. Yeah. Okay, and here I have a convex lens. Okay, and let's see what happens to these rays. Yeah, it's a 3 parallel beams of light, right? Okay, and let's see if I actually put it here. Yeah, so you can see I can actually manipulate. That's how I can manipulate light. Yeah, by going through matter. Yeah, so the moment you put in that lens, yeah, it's a plastic piece of plastic which is bent in the form of a lens. Yeah, bent in the form of a lens, or cut in a form of a lens. I can actually see I can change the orientation, where it goes. Yeah, so on and so forth. Yeah, and that's a convex lens. Yeah. By the way, you guys are most welcome to come and play with it. Yeah, it's no point me playing with it. I've played with it enough. Yeah. So that's a convex lens, which is used to correct myopia in eyes. Okay, and since someone was actually interested in the names of them, yeah, hypermetropia is a long-sightedness. This is also corrected, but by a concave lens. Yeah, and the moment you have a concave lens, you see how light behaves very differently. Instead of converging, yeah, it starts diverging. And again, you can absolutely manipulate, yeah, how this light will behave, yeah, by changing the orientation. And also, not only changing orientation, you can also change the curvature of these lenses. We can change the curvature of these lenses. Yeah, so these 2 lenses here have slightly different curvature. We can see what's happening there. Okay, and okay, so before I go into that, yeah, so this is a convex lens and this is a concave lens. If I put it together, it kind of it's not brilliantly correcting, but it kind of corrects for each other. And so if this is going to make light diverge, let's see if I do that, then can it again bring it back to its parallel beam? You see, it does it. Okay, so a combination of the right curvature of the convex and the concave lenses, yeah, does the maximum amount of correction. Yeah, so that's what I wanted to show. Between 2 concave lenses, so for example, this is of one curvature, this is of a slightly different curvature. And if you can notice it on the other side, you can also see, I don't know whether you can actually see it very clearly, but on the back side of the lens, you can see the point from where the virtual image is actually going to form. You can see the back tracing of the rays. Yeah, you can see the back tracing of the rays which is happening here. Yeah, so the rays are coming like so and then diverging. But if you trace these lines back, you can pretty much see that's where it is kind of originating from. Yeah, you can see these faint lines on either side. Yeah, so that's that. The other very interesting thing comes. If I take a semicircle, yeah, a semicircle. Okay, if I take the semicircle and let's say I shine light diametrically along the radius. Yeah, I shine light along the radius. Yeah, it just goes through practically undisturbed. It has a bit of lensing effect though, but if I kind of position it very carefully, it does that. Okay. Now, what I'm going to do is, keeping the center of the semicircle fixed, I'm going to rotate it. Okay, I'm going to rotate this semicircle such that the angle of incidence changes. Okay, and especially notice the angle of incidence in the plastic air interface where the light is going out, not going in. Okay, which is this interface. Okay, so if I keep this point fixed and I kind of rotate it, and you can see that it is actually getting deviated. Okay, it is actually getting deviated. And now see what will happen. Suddenly, it gets reflected rather than transmitted. You must have read about this. That's right. You cross the critical angle of incidence when light passes from a denser media to a rarer media. Yeah. And if the angle of incidence is higher than the critical angle, or what is known as the critical angle, then you'll get total internal reflection. Yeah. So you can see that even without a mirror, you can actually have reflection. Yeah. And this is very famously exploited in the context of periscopes. Hopefully most of you have heard of periscopes, right? Yeah. What is a periscope? No one? Yeah. Go ahead. It's in a... That's right. Right. That's right. And it is used where? It's used in submarines to look at objects above the sea level, yeah, when you are actually below. But you can do the same with bunkers if you are playing around with bunkers. Okay, so the same principle of total internal reflection can actually be seen much more easily if I have a right angle prism. Yeah, this is a right angle prism. And let's see what happens. Let's see what happens if I shine light on one of the vertical edges. Yeah, on the edge, which is not the hypotenuse, on one of these sides. On one of these sides, it will be easier. Okay. Oh, there's. Okay. So you can see, you can actually, and you can even change the angle of reflection by tilting this this thing. Yeah. So you see, I don't have a mirror, but still I am getting kind of reflection. As long as I'm above the critical angle. Yeah. That's the crux of the story. Okay, the last of these thing is basically a small block of plastic. It is just a cube, just rectangular cuboid kind of thing. Right? No, it's not glass. It's made of plastic. It's not glass. It's like a glass slab, but the material is not glass. It's plastic. Yeah, it's plastic. Yeah. And obviously, if I push in light here, nothing very fancy happens, except it just goes in through, because it's normal incidence, it just passes light through. But look at what happens when I kind of, start rotating it. The moment I start rotating it, yeah, you see, again, total internal reflection takes place on this boundary, and light is kind of, coupled here. And if I actually push in 3 light beams, you can see, yeah, a bit difficult probably with this. Let's try that. Yeah, okay. This is a slightly of a different dimension. And you can see what happens that once it's not working. I'll stick to one. What I wanted to show was that this total internal reflection that you are seeing here is also the mechanism by which optical fibers work. Yeah, so you can imagine if this block was longer and longer, yeah, it would have kind of, so if I, let's say, push it here, it will again reflect it back. Yeah, so if I have a long chain of deformable glass, which is a fiber, yeah, I can actually bend the light beam and keep it always confined within the material and not let it leak out at all. Yeah, that's how an optical fiber works. Okay, you're most welcome to come and try it if you want. Let's take this off. It's again gone into oscillation.